All right, let's pick up where we left off. So we're going to talk about arc length. The arc length just refers to a portion of the circumference. So what we have here, once this, there we go. So what we've got going on here, this right here is the length of an arc. They're calling it S. And the length of an arc S subtended by an angle with a measure of theta in radians. That's going to be given by this formula. So we'll write a little bigger here. S equals R times theta, where theta is in radians. So if you do the radius times the angle in radians, that will give you the length of the arc. So given a circle of radius r, you calculate the length of S. If you need to, convert the angle to radians first and then multiply it by the radius, and that will give you the length of the arc. So in this example, they say it's a 215-degree angle. Remember that we have our conversion here. We're going to do theta over 180 is equivalent to theta r over pi. So if this is 215, we're going to do 215 divided by 180. That equals theta r over pi. If we do 215 divided by 180, that is equivalent to 1.1944 repeating. So like we did before, you do math and then select the frac thing. That's 43 over 36. So this is 43 over 36. And that equals theta r over pi. We need to multiply both sides by pi. And if you do so, you get 43 pi over 36. That is the angle in radians. So then take that angle, multiply it by the radius, which is 10. 43 pi over 36 times 10 is going to give you 430 pi over 36. And let's see here, that would be, they don't tell us just how many units. So we can't say that's inches or feet or anything. So we'll just say it's that many units. If you do 430 times pi and then divide that by 36 as a decimal, that is approximately 37.52 units. All right. Let's see what we have next. So the area of a sector, so this is basically a slice of pie, if you will. So that's going to be 1/2 theta r squared is the formula to find that. We'll write it nice and big, 1/2 theta r squared. As before, this is specific to the angle being measured in radians. So if the angle is not in radians, take a minute to change it to radians first. So if we look here, so that's what they say here, convert to radians, multiply by half, and then square the radius, and then multiply by the angle. So what do we have in this example? In a central pivot irrigation, a large irrigation pipe on wheels rotates around the center pipe. It has a radius of 400. So we know R equals 400. Let's see. She can only do 150,000 square meters per day. What angle do we need to use? And they say write it as a radian rounded to 2 decimal places. So our goal is to have the area be 150,000. That's going to come from 1/2 times some angle theta times the radius squared. So that's 400 squared. 400 squared is the number 160,000. So that's 1/2 times 160,000 times theta. And then let's see here, if we multiply that by 1/2, now we have 80,000. And then if we divide both sides by 80,000, let's see here, 150,000 divided by 80,000. That's going to give you 1.875. So theta is 1.875. They do tell us to round to 2 decimal places. So we're going to round this up to 1.88 radians. So that would be the angle that you would need to subtend or cover to have a sector, a circular wedge, to have that cover 150,000 square units. All right, what else do we have going on here? So angular speed and linear speed. So in very broad terms, think of this like there's the speedometer on the car that tells you like how fast you're going as a linear speed. That's going to tell you miles per hour. You might have also noticed that on a lot of cars, they have like an RPM gauge, which is showing you the revolutions per minute, which is telling you how quickly the gears are spinning. And of course, if your car changes gears, it can adjust what the RPMs are going to be. And so the revolutions per minute, the RPM, that's going to be a reference to the angular speed of how quickly it's spinning and how that translates into a linear speed, which is the distance traveled per unit of time t. Now, when you're measuring in radians per unit of time, the relationship between linear speed and angular speed is this. The linear speed, which is v, is the radius r multiplied by the angular speed, which is, it looks like W, but this is actually the Greek letter omega of all things. It looks a lot like a W, but it's actually a lowercase omega in the Greek alphabet. But anyway, if you just want to call it W, that's fine. All right, so let's see what we have here. So how to do this. So first of all, like all the others, make sure that you have the measure of the angle in radians. Then you need to divide the radians by the amount of time that has elapsed. So you do theta divided by the time. That will be the radians per time unit. And then recall that V equals R omega, or RW, if you will. So here we have a water wheel. It completes one rotation every 5 seconds. So they want the angular speed in radians per second. So going back to the beginning here, if you have one rotation, remember that that is 2 pi radians. It's just once around the circle. So this is going to be 2 pi, and then the t is going to be 5 seconds. The angle, we already have the angle in radians. So W, or omega, is going to be 2 pi divided by 5. So that would be the exact value. If you wanted to turn that into a decimal, you could do 2 times pi and then divide it by 5. Let's see, 2 times pi divided by 5, that would be 1.26 if you rounded it off. 1.26, and that would be radians per second. And we can tell it's in seconds because this is 5 seconds, which is the unit of time. An old vinyl record is played on a turntable rotating clockwise at 45 rotations per minute. Find the angular speed in radians per second. Okay, 45 rotations. So 45 times 2 pi, because remember, one rotation equals 2 pi radians. So this time we're going to do 45 times 2 pi, which is going to be 90 pi. Also notice that's per minute. So what we're going to do is say 90 pi per 1 minute. Now our goal is to have it be, this is 90 pi radians, and we've got it in terms of minutes. We want to have it in terms of seconds. So the way you would do that, if this is minutes down here, we need minutes up here. And then minutes is going to convert to seconds. So we happen to know that 60 seconds is equivalent to 1 minute. By doing it this way, minutes can cancel out minutes, because when you're converting units like this, you want to have one unit on the bottom and you need to have another unit on the top and have them sort of oriented diagonally so that they will cancel each other out, one from the top, one from the bottom. So if we do that, we're going to end up with 90 pi over 60, and that'll be radians per second. And let's see, you can reduce 90 over 60, that's 1.5, also known as 3/2. So that's 3 pi over 2 radians per second. That would be the exact answer. If you wanted to round it off, Let's try that again. If you wanted to round it off, you could do 3 times pi divided by 2, which is 4.71. So that would be a slightly different way. You could write your answer, 4.71 radians per second. So this kind of just depends, do they tell you to round it or do they ask for an exact answer? When I write questions, I try to spell out as clearly as possible what it is I want. So if I want you to round, I will tell you to round. Otherwise, the exact answer is kind of what's preferred. All right, so if you're given the radius of a circle, an angle of rotation, and a length of elapsed time, you can determine the linear speed. So as always, you're going to convert to radians. Divide the total rotation by the elapsed time. So you divide the radians by time, which we were doing earlier. That's what this is. Then you're going to multiply the angular speed by the length of the radius. You're going to multiply the radius, and that'll give you V, which is the linear speed. So a bicycle has wheels that are 28 inches in diameter. Fun fact, that's the diameter. If you cut that number in half, that'll give you the radius. So we know the radius is 14. A tachometer tells us it's going to be rotating 180 RPM, which is revolutions per minute. So 1 revolution equals 2 pi radians, as we've said before. So we want the speed of this bicycle, and this is inches. So the speed is going to be miles per hour. That's typically how we measure speeds. So how are we going to do this? Well, first off, we need to do 180 times 2 pi, and then we're going to divide that by 1 minute. Then we need to, since we're doing this in hours, we need to say, okay, that's minute. We're going to put that with minute. And then we want to convert that to hour. We know there are 60 minutes in 1 hour. So if we do this, the minutes are going to cancel each other out. 180 times 2 times pi, and then also multiply that by 60. You'll end up with 67. Let's go back to red here. That will be 67,858.40. And that is going to be inches per hour. So now what we need to do is change that to miles. So if we're going to change that to miles, we're going to do 67,858.40. That's inches per hour. We're going to multiply this. I know that there are 12 inches in 1 foot. And again, notice inches is up here, which means I need inches down here. Now I have feet up here, which means I need feet down here. If you don't happen to know this, there are 5,280 feet in 1 mile. So then we can turn this into miles per hour. So this is going to be 67858.40. And then we need to divide that by 12 times 5280. So if we work out what that is, we put that stuff in parentheses here, 12 times 5280. That will give you the number 1.07. That is 1.07 miles per hour. And then we also need to multiply that by the radius. So this is W, or omega, if you will. So W is 1.07 miles per hour. And then what we need to do is we need to say, okay, we're going to do V equals R, which is 14 times W, which is 1.07. And when we do that, take that decimal times 1. And that's basically 14.99. It's basically 15 miles per hour. So the speed that the, what is this? The bicycle is going 15 miles per hour. It's 14.99, so basically 15. Okay, looks like we've got one thing left here. A satellite is rotating around the Earth at 0.25 radians per hour at an altitude of 242 kilometers above Earth. The radius of the Earth is 6378 kilometers. Find the linear speed of the satellite in kilometers per hour. Now, the good news is we don't have a lot of unit conversions, because you'll notice we have radians per hour. That is going to be the angular speed. We have an altitude of 242 above Earth, and then we also have the radius of Earth. So basically what's happening here, we'll do it in blue because that would make sense for drawing the Earth in blue. Yes, that's kind of a lumpy Earth, but we'll go with it. So the center of the Earth is right here. There's the journey to the center of the Earth. And what is that? That's 6378. That's the radius of the Earth. And then if we go another 242 kilometers, this drawing is not to scale, just so you know. Let's maybe write that a little more neatly, maybe. There's 242. And then when we get out there, maybe we'll put it in black, and we've got like a little, I don't know, satellite thingy that's like floating around. There you go. There's the satellite. And so anyway, the big takeaway from this is if you put these together, that will be the value of R. So the radius is that. So R is 6378 plus 242. What, pray tell, let's write so it's not slanted. 6378 plus 242 is 6620. There you go, 6620, and that is kilometers. So then what's happening? We want the linear speed, which is V, that equals R times W, R times omega. So what? R is 6620. Omega is 0.25. And if we multiply that by 0.25, we get 1655. So 1655, and that'll be kilometers per hour. And there you have it. So that is how fast the satellite is spinning around the Earth. And that's really fast. Okay, so that is the end of that section. And so we will pick up with the next part on our next class. See you then.